Hey everyone, Zach here again, and I've got a quick update on the topic of my previous video. Previously, I showed off this tool that I've been working on to improve the workflow of level design, level generation for the game I'm working on, and I had kind of a shopping list of items that I wanted to add to that I touched on briefly at the end of that video. And I've been working for about a week since I posted that last video on a couple of those key details that will help me take the steps to make this actually a functional editor, and I wanted to show those off really quick. So I've got my basic camera movement here. I can look around with the mouse now, and I can still move around. And what I've done is I've added a simple screen space to world space conversion of the mouse. So the mouse is moving on the screen in an X and a Y. We've got the positive X moving left to right and the positive Y from top down. And what I really needed was a way to convert the mouse 2D position into a 3D world position and then be able to cast a ray from the camera to that world position or through that world position and then be able to determine if it hits any objects within the world. This would be useful for things like highlighting an object of interest to select it so that I can edit its properties, to be able to click on an object to get a transform gizmo to pop up so I can move it around the world. All kinds of things would make it really useful. Even for beyond this project, potentially even doing things like a menu system. If I was going to do a UI or a menu in Vulkan purely, I could use this method to interact with a 3D menu system where maybe the text is drawn on a billboard or something and you want to be able to highlight that billboard. All kinds of things. It's a really useful task. And I've got it working. And what I can do is if I hit the E key, I'm going to draw a line from the camera through the mouse. And I've already done it, and you can't see it. If I back up, though, we'll see it pop up. So now I have this orange line that seems to kind of point towards the tip of the mouse. And I'm just moving forward and backwards of the camera. So it's just moving along the camera's Z vector. But if I slide over, we can see that it's not moving, it's not following the mouse, but it is just a line through space. So what we have is this is where the camera was. The mouse would have been somewhere around here, and we just shot a ray right through it, and we're drawing that ray. So this is cool, but it doesn't really do much for me. But I'm actually checking this every frame. The mouse position is being updated, and this ray is just simply generated by the mouse position times 1,000 or something minus the camera position gives us the line segment, or we use the camera position as the origin and then the mouse position minus the camera position as the direction for a ray that we can shoot. And what we do is we're actually checking collision against all the objects each frame also. So if I hover over one of these, they now turn orange when the mouse is over them. It's pretty robust, works pretty well. And what's actually happening is this ray is just being shot through it, and I'm doing a basic collision test on these objects. Right now, I don't have anything like bounding boxes or any spatial partitioning to make it faster. It is just doing the raw brute force, check each triangle of the object and return the closest hit. So it's not going to be the fastest thing in the world for a large scene, but it does work. And I can hover over any of them and get them to turn orange, highlighted. And we can see if I hit E again, you can see where it struck that object. And it works pretty well. It works from any direction. I had some fun getting this to work. The unproject should have been as simple as just reversing the process of the projection. So the camera times the view matrix times the projection matrix times the model matrix multiplied by the point is how you would project a point onto the screen. to unproject it from screen space back into world space, you just do the inverse of that. So you basically multiply the point by the inverse of that model view projection matrix. And it worked at first when I was at the origin. So if I was at 0, 0, which is where I am now, looking down the z vector, it worked great and I could look and see it. But if I came out here somewhere and tried to shoot it, now it works great, but it wasn't working. And I tinkered around with where on the z-axis that 2D point was, because to get from 2D to 3D, we have to give it a starting point, a starting z value, where in the depth buffer the point is. And I tried -1, 1, 0. I tried all kinds of points. I figured it should be on the closest frustum, which was 0.1 is the near plane that I'm using, and that didn't work. And I guess I didn't actually try 1, because finally when I set it to 1, it started working. And I think the reason is I'm not sure if I had the depth buffer backwards. I don't know how I was viewing the device space. The screen space just wasn't quite right in the Z direction, and finally got that worked out. I actually had to ask on Stack Exchange, and unfortunately nobody got back to me, but just a little trial and error and thinking a little harder about where that point would lie in the projected space, I finally got it working. So I can generate the maze still, and the cool thing is that it works for all of the walls in the maze. And you can see it gets a little choppy. It's not quite as responsive, and that's because I'm not doing any optimized collision detection. This is just brute force checking all of the walls in the maze, so it is a little slow, but it runs pretty good for a maze of this size, which should be 50 by 50. And that's kind of surprising. I expected this to just really crawl, but thankfully these walls are simple geometry. There's, you know, two triangles times 6 sides, so there's 12 triangles total to check for each one. But overall, I thought it would run a lot slower. And the nice thing is that this is still instance rendered, so each one of these is actually just an instance. And I set it up so that you can pass a instance transform into the ray query, so that you can take one mesh that still essentially lives in its model space and then add an extra transform, a world space transform to it as well. So it'll do things like its world space position as well as its world space rotation and scale and things like that will all factor into it. And it's just simply adding the transform matrix into the equation, which is defaulted to an identity matrix, so you can skip it if you want. And it works good. Then I don't have to modify how I'm handling the data, how I'm processing the instance buffer and passing the instance buffer to the rendering pipeline. I can kind of keep them separate, and it works great. So this was really cool to get running in a couple days. I've been working pretty hard on it. I only have so much time after work in between hobbies and spending time with family, but I've been working on it pretty hard, thinking pretty critically about the math involved, and I really enjoyed just watching this come to life and getting to see it actually work. This is a pretty impressive feat for me. It's something that I've always thought about as being really difficult to implement, and thankfully it was actually pretty straightforward and simple. So I'll have some code on the blog page about this once this video is published. I'll publish the blog page as well, and I'll put some code snippets in. We've got some pretty basic stuff. The ray intersection test is the typical plane intersection and then narrowing it down to a triangle. We do the transformation first so that we can take it from an instance model to its kind of world space transform. And then it's just the simple ray intersecting a plane and then narrowing it down to a triangle using the cross product and dot product. If you're used to collision checks, this is probably not going to be new to you. It should be pretty simple. It's in all the all the basic books on how to do simple triangle ray testing. And the line segment is basically the same thing. It's just a little bit different in how the math is calculated. And then I've also got the code for the screen space unproject. And this is pretty simple. Like I said, we're just converting the mouse space into the NDC coordinates and then doing the reverse of the projection matrix. And then we have to divide by W to get the right full position. And then we just update the global world space mouse, and then we can use it for whatever. And it's simple, pretty easy, and it just kind of fits right in front of the camera update and the rendering stuff. So it's just kind of sneaks right in there, and it's not too bad and simple, easy. So thanks for watching, and don't forget to check out the code post when it's there, and I hope to catch you later.